Hello everyone, thank you so much for joining us on our webinar today. Let's go ahead and get started. Today's webinar is going to be on final element integration, how to become certified in final element integration, what to look for in certified integrated final element programs, and how those can affect failure rates. For those of you that are new to our webinars or have not yet met me, it's nice to meet you. My name is Loren Stewart. I work here at exida, mostly with our mechanical customers. I work a lot with our valves, actuators, solenoids customers, helping them achieve IEC 61508 certification, making sure that they understand everything in the standards that they need to apply in their everyday life. I also work with exida Academy as one of the instructors. I do courses and teachings and a lot of these webinars. In case you are unfamiliar with exida or you're new to who exida is, we do everything when it comes to functional safety. If you are an OEM, we're all the way in the beginning helping you understand what's going on in IEC 61508, which we will be talking a lot about today. We can help you achieve certification. We have tools, we have blogs, webinars, white papers, all types of supporting and training that we can help you the whole way through to the people using those certified devices or the end users. We have people that can help you as well. We have tools, we have calculations, consultants, trainings, all sorts of things to help you and make your life easier as well, and everyone in between. So if you have anything to do with functional safety, alarm management, or cybersecurity, we have the experts in place to get you the knowledge that you need to really ease your job. There we go. No matter where you are, where your customers are, where your products are coming from, where your supply is coming from, it doesn't matter. We have somebody close by to help you out. We have experts in alarm management, functional safety, cybersecurity, worldwide, that we have someone that can get to anywhere that needs to be, and quickly if need be as well. So no matter where you are, we can help you out. We can train, we can come to you, you can come to us, however you'd like us to help. One thing that I'm really proud that exida does, sorry for the pun, but we like to be an open book. No matter what we are researching, what our processes and our procedures are, everything we are investigating and figuring out, we figure that we have the most up-to-date information on functional safety. And if we have this knowledge, we need to get that information out there. If we get the information out, we're actually going to make the world safer instead of just hoarding all of that knowledge and having it to ourselves. That's not useful. So we publish a ton. We have these free webinars that you know of that are on YouTube and our website. We have free white papers you can download, blogs that we can interact between. We have books, we go to conferences, we go to conventions, we give speeches and presentations. We have our database and our failure rates all published. Everything we have, we get that information out. So if you have any questions on what we're doing, you just have to look around on everything that we're publishing lately. But let's get into why you're really here, today's webinar. So in the integrated process, when we're putting together a final element for integration, there's a couple of different ways that can be done. The simplest way is randomly selecting a valve, randomly selecting an actuator, and randomly selecting a solenoid, piecing them together, hoping they work, and shipping it out. That's one type of integration. That's not what we're going to be talking about today. We're talking about the people that are actually doing integration, the people that are doing a good engineering process and they have procedures created for integration and actually used, not just documented. They look into field failures of integration, validation and verification, making sure it's tested before it's shipped. All of those fun things we're going to be diving into and looking at and showing how if you do those things, that a portion of failure rates, each individual device or the final element assembly failure rate can be lowered. And we're going to look at exactly why that happens. Before we really get started, if you have any questions throughout the webinar, please feel free to type them in the questions panel of the GoToWebinar control panel. I am not the greatest at stopping my presentation and looking to see if there's questions. I usually get on a roll talking and just continue. However, I will leave time at the end, so if you do have any, please feel free to write them in, and I'll take a couple moments at the end to see if there's any questions. If you are here today for this webinar, you'll get a copy of the slides sent to you, and this webinar will be recorded and up on our YouTube channel and our exida homepage as well. So I want to start this webinar off by looking at, well, what's the big deal? Why is this really important? Well, when we were looking at field failure data, we found that as great as the functional safety standards are, as great as the processes and procedures and the devices we are buying are, we're still having failures in the real world situations. We're still seeing problems occurring. When we investigated, when it's looked at, why are these happening? Well, there's two main observed failures. And this is especially zoomed in on our final elements and our final elements in our safety systems or in our SIFs. Those two key fundamental failures are insufficient force, meaning if you have your safety system protecting against a process flow and a valve needs to close off that flow if there's a hazard or a situation that occurred to stop the process flow and stop the condition. However, if this failure occurs that we see, there's not enough force to close that valve. So whether there is some sort of not enough torque built up, or there was stiction, cold welding, corrosion, somehow there was not enough force to move that valve. Obviously, the valve needs to close to shut down the process. That's an issue. Another major failure that was observed is that in mechanical failure, in mechanical components such as your final elements, there's seeing stresses beyond their yield strength. So you go back to think of when we first learned engineering and we talk about stress strength. At some point, whenever stress overcomes the strength, you're going to have an issue. So these are the two major problems that keep occurring in real world situations. And at this point, this day and age, we stop and ask ourselves, well, how is this still happening? We have standards in place. People are getting their devices certified. People are still doing calculations and putting those certified devices in their safety systems. How are we still getting weaknesses in SIL rated assemblies? So we're engineers, what do? We do root cause analysis. We wanted to investigate, why is this happening? This shouldn't happen. We figured out there were different reasons of why. There's, of course, reliability is not met, performance of not being met, the valve not being able to actually function, mechanical failures. All of these possibilities can lead to possibly dangerous occurrences in the safety system and final elements. A study was done of actual accidents involving control systems, real life accidents, not just on pen and paper, not just theoretical, but real life, what's going on. The study was done by the UK. And as you can see, there were issues involved in the entire lifespan of the safety system. So once the safety system is specified, you can see there were 44% of the dangerous failures or those accidents happen because of poor specification. So that's completely on the front end of things. That's in engineering and design. That's way before that SIF is ever protecting against anything. There are, of course, other issues throughout for the SIF. In design and implementation, 15%, installation and commissioning errors at 6%. And then something that if you are a OEM, you have no control over, the operation and maintenance and changes after commissioning. However, if you're an end user, this is where you highlight. This is where you can come into play. 15% of accidents happen because things were not maintained or operated correctly. There wasn't knowledge or it wasn't properly taken care of. And then 20% of accidents occurred because of changes and modifications happening after the systems were in place and up and running. Whether people didn't understand the importance of a SIF and their safety system, or errors just happen, but 20% of those happen because of changes after the fact of engineering. So as you can see, there is room for improvement no matter where you are involved. If you are a device manufacturer, an OEM, you can really take responsibility in the front end and try and get your customers more information, get them the specification details over information that they need to properly size, to properly make sure that this equipment can prevent against whichever hazard that they are protecting against. If you, the whole way through, if you are an operation or an end user, where can you play in changes in operation and maintenance? Both OEMs and end users need to follow safety life cycles and functional safety. That's where the standards come into play. If you're on this webinar, you've probably heard about some current functional safety standards. We have IEC 61508, which is that kind of umbrella standard, that base publication in functional safety. It is in the terms of OEMs. So it's talking, when it talks about its life cycle, it's the life cycle of how to make your device, how to design your device, the whole way to what information you need to get your customers. Underneath IEC 61508 comes other more specific industrial standards. Say if you are in machinery, automotive, nuclear, they all have their specific standards. And the same with the process industry sector. You have IEC 61511 as the process industry. So that is very similar to IEC 61508. However, it's in the language or the terms or the point of view of end users. So it once again has the functional safety life cycle, but its life cycle is talking more of the life cycle of the SIF and how the safety system is going to protect against a hazard. In this webinar, we're going to be talking kind of back and forth between IEC 61508 and the OEM standards, and the IEC 61511 and the end user standards. We're going to start with IEC 61508. And as I said, it's kind of that umbrella standard. It was the first real functional safety standard out there that was concentrated just on functional safety and not a bunch of other things as well. When you are getting a product certified, no matter if you're doing a simple mechanical device like a valve or a highly complex coded software element that is very complex, you're going to have the same process and project steps. You're going to go through the project, make sure that all of the requirements of IEC 61508 have been met for whichever SIL level you're trying to achieve. You're going to also do an FMEDA to get the failure rates for your individual device. You're going to also look at things like proof test coverage, mission time, useful life, all of that stuff. But at the end of the product, if all of the requirements of the standard have been met, you receive a report, or at this point, probably multiple reports, and a certificate. And that certificate has your systematic capability, your architectural constraints, and especially those failure rates on the back. Now, as I said, depending on how complex your device or element is, you might have a little more work to do. If you're a valve, you're not going to necessarily have software and coding going on. However, this goes along the same steps of the safety life cycle in the standard. On the other hand, we have IEC 61511. Remember, this is the end user's point of view. They say a lot of the same things, however, it's just worded differently. Same type of safety life cycle. It's broken up into, once again, the analysis, realization, and operation phase. However, we're talking about the entire SIF instead of just the device. In both safety life cycles, both standards really hone in on documentation, how it doesn't matter what you're doing, if it's not documented, it doesn't count, and also how you're dealing with modifications. You don't want to just change something and not consider how that changes might affect others, pieces of the device or other pieces of that SIF. When we think about functional safety from the end user's point of view and the SIF point of view, instead of just thinking of the what is happening or what could go wrong just in that valve, they're instead looking at what can go wrong from a hazard point of view. So first of all, we want to know what possibly can go wrong. Say we want to look at what the process is and what you are protecting against. What really is the risk? Are you in an ammonia plant in the middle of a cornfield with very toxic, very dangerous substance? Or are you generating power in the middle of a city right next door to an elementary school? No matter what your condition is, no matter what the risk of the process is, you want to consider what can possibly go wrong. And the end users do that through HAZOPs or PHAs. After we figured out what can go wrong, we want to know, well, if that goes wrong, how bad will it be? And that's where the layer of protection analysis, or LOPA, comes into play. We then looked at, well, to protect against that, what needs to be done? And we look at all safety requirements that need to be met for that SIF. And then we think, well, if those pieces of equipment are put into place to protect against that hazard, against that bad thing happening, is it actually going to do its job? How reliable really is it? Then, when we are in the safety life cycle, we want to keep this process going. If you make changes, modification, how to sustain your SIL rating, how to sustain those failure rates, how to keep that hazard from happening, that risk to be low. So as you can see, the end users are really thinking in terms of their process, of their plant, of what they're protecting against, whereas the manufacturers, the OEMs, are really thinking of their device individually. And a lot of times where we're seeing accidents happen, where we're seeing room for improvement to occur, is where kind of the right hand isn't talking to the left hand. The OEMs have this great information. They might be trying to get it out, or the end users might not be getting the information. They might not know all of the information they need to have a well-designed system. A lot of people are arguing that there's a gap in between IEC 61508 and 511. There's some sort of like no man's land in between the two standards that integration kind of is falling in between. And when we think about that, we in functional safety think of the Swiss cheese diagram. Well, what is that? Well, no matter how many layers of protection you may have, nothing's going to be perfect. And if you have enough of those holes, eventually those holes are going to line up and an accident could occur. Those holes can be built in, or those holes can be brought in. However, we need to make sure that all of the pieces of integration are not going to line up to cause that accident or that unwanted hazard from occurring. So where IEC 61508 and IEC 61511 intersect is, yes, we can think of that hazard identification, but also bring in the items of IEC 61508, such as the FMEDA or the FMEDA for the final element integration. We want to make a safety requirements not just for the entire SIF, but for those final elements. When we talk about where a lot of those issues, where a lot of problems occur, where those dangerous failures are occurring, the spotlight's on the final elements. We see often that there's room for improvement there. So if we can have a special safety requirement specification just for the final elements, we can get that very much improved. And that really can sustain the SIL capability. It is imperative that integration is getting as much rigor and as much attention as all of the other devices that are going into the safety system. You know, when we think about our SIFs in place, what's protecting against that hazard from happening, it's only as good as its weakest link. So if you're just throwing final elements together, not integrating them well, and putting that into a safety system, you're not going to get the type of results that the high quality devices that you're using would assume. As I mentioned, one key piece of information is the SRS, or the Safety Requirements Specification. We have a safety requirement specification from IEC 61508. It's the information about how the device is going to act, how it might fail in different environments and different operations. It could bind, it could have a loss of drive, it could have dangerous failures or safe failures. On the other hand, we have IEC 61511, the end user's view, that are just thinking of that operation. Well, I don't care if it binds or if it lost or the safe or dangerous what you're talking about. I don't care about that. I want to know the valve is going to close when I need it to close. I want to know that the valve isn't going to leak. So there needs to be come together and have common a common document with common language for functional failure modes and final element requirements. As I said, when you think on the end user's level of IEC 61511, we're thinking of what that device can do. So when we're talking about an SRS and what's important pieces of information for that document, the end user wants to know if the valve needs to close, it can do so. If it doesn't need to leak, it will make sure to not. If it is a tight shutoff application, it can achieve that low level of leakage. If the valve needs to close within 1 second, it can do that job when required. Usually, when we talk about an SRS, we talk about it for the SIF overall. It's going to have a lot more information in it on the overall SIFs. It might say, well, we have a process, a hazardous process going through this piping. A ball valve is going to be in place. It needs to close on trip. If there is a hazard, trip happens, the valve closes on command. The valve needs to be able to have a tight shutoff or a minimum leakage requirement of a class 4 leakage. It needs to do the final element, or that valve needs to close fast enough that the SIF functional safety time is 15 seconds. So it's not just the valve closes in 15 seconds. The whole safety loop needs to react and shut down within that safety time. Next, we want to look at how it's going to be plumbed, de-energized, or energized to trip, the SIL requirements or the systematic requirements for all the devices in the SIF, proof testing, proof test coverage, proof test duration, proof test instructions, and any other requirements. So what's important for the final element SRS? Well, we need to think on both the OEM and the end user side. We need to have common language and we need to have common pieces of information that can rely back and forth to each other, such as any functional safety requirements, any system design, any device requirements, anything for the factory acceptance test or site acceptance test. As we said before, proof testing, proof test guidelines, any other operation and maintenance guidelines, in addition to things like the failure rates and the process safety time. Once again, it's not just good enough to take a valve, take an actuator, solenoid, stick them together and throw them out there. Integration needs to have that same rigor and that same process, the same procedures as just a device that is being thrown into this SIF. Or even if you think of it from an end user's point of view, they're doing all of these calculations to make sure that these devices will work. We want to make sure the integrated final elements for them will be reliable as well. So just as with IEC 61508, and 511, we talk about the functional safety management, to have a plan, to have a process in place. We talk about to have the safety requirement specs or the SRS. So all of the really important details are documented and realized in one location. We're going to look at validation and verification. As I mentioned before, both standards have a very high stress on documentation. Basically, if you didn't document it, you didn't do it. And to not only do this, but to get the information out to the end users or the people that really need it, to communicate this information well in something like a safety manual. So, as I said, we need to do as much as we would do for a device as for the integration. We don't just let the integration go off easy. Just as you would look at design requirements for each device, you need to look at them for the integration as well. Making sure things like the actuator is sized properly, that you know all torque requirements, not just the common ones, that you've designed coupling brackets for strength. You're not just grabbing a piece of scrap metal off of your neighbor's tool bench and bolting it on, that you've done analysis from this, that you're looking at the system design and looking at diagnostics, looking at SIL verification. All of this is extremely important. I mentioned torque. There's multiple different torques. Yes, there's the torque that you need to work the actuator, work the valve, but there's more than just that. There's breakaway torque. We also have your dynamic torques. We're going to look at the friction, make sure you're in the same application, the same operation, make sure it's time dependent, whether you have low demand or high demand, making sure that you have that apples to apples comparison. Another portion of the design review that you need to do for integration is the integration. When your people are putting it together, are there procedures? Are there fixtures? Are there instructions? Does everybody know what they're doing? Or is it just bolting something together and putting it out there? Are you testing it? When you are testing it, are there instructions for testing? Are there pass-fail criteria? If something fails, do your guys on the shop floor know what to do? Do they send it back and have it reworked, or is it just kind of left there? Then, after all of that, we come to validation and verification. We look at the integration of the final assembly just as we would look at each individual device. We would look at validation and verification for each device. We want to verify each requirement and then validate each top device requirements for the entire integrated assembly. We also want to consider SIL verification. I'm just going to briefly mention the 3 barriers that you need to pass for SIL verification. And the IEC 61508 and 511 talk about these 3 barriers, or the kind of hurdles you need to achieve for compliance with the standard. You need to consider random failures, or your failure rates, your PFD average calculations, your architectural constraints or your hardware fault tolerance, and your systematic capability. We check all 3 of these barriers to make sure each individual devices, along with the integrated assembly, passes all 3 of these barriers. If you want more information on these barriers, we have webinars just on the 3 barriers topics. We have webinars just on PFD average, just on failure rates, just on hardware fault tolerance or architectural constraint, and just on systematic capability. Each of those topics is a whole mind of its own. So if you want more, go to our YouTube channel or our website, and you can dive into more of what those are. But unfortunately, I'm not going to have enough time today to dive into each of those. However, with the SIL verification, as I said, we need to think of both all the components of the assembly and the final element assembly, integrated assembly overall. It's not just good enough for you to verify the valve, the actuator, the solenoid. You need to think of everything that could be included. Are you doing coupling, brackets, switches, filters, regulators? Any of that may be in this final element integrated assembly. You need to be considering all of those pieces of equipment. Once again, your safety system in your building is going to be only as good as its weakest link. You could have the top of the line, the sports car, the best of the best valve and the best of the best actuator. But if you mount them together with brackets that is just sheet metal that breaks and the valve and actuator fall apart from each other, doesn't matter how great they would be. It won't do its job. So when you do the SIL verification, all components need to be included. When we talk about verification and validation of the final element integrated assembly, we follow the steps of the functional safety life cycle and all of the requirements in the standards, just as we would as for the device certification. From each requirement of the standard, there is then a verification and validation test or technique along with documentation to prove that. Now, if you are doing all of this wonderful, great stuff, then your failure rates should show it as well. When we calculate failure rates for each device, we have a little cushion built in for integrated and integration failures. From that study, we know that specification and are a huge amount of failures, and as long as we have humans doing work, humans doing calculations, there's going to be errors and failures from that. So if you are going above and beyond, if you're doing the validation, the verification, if you're figuring out all of the torques beforehand and taking all of that into consideration, well, the associated failure rates, or the failure rates and the associated margin or room or buffer can be eliminated as well. So where do the failure rates come from? Well, first of all, you have to make sure each device has valid failure rates in a detailed comparison. Make sure it's the same application in the same environment. If you are don't compare a cabinet mounted, like a controlled climate, clean service valve with one that is going to be a mile below C with severe service run through it. It's not an apples to apples comparison. Make sure you know where your failure rates are coming from. Same with low demand and high demand mode of operation. If your valve is only moving, or hopefully only moving once, or you're only seeing a demand of once a year or once a month, don't take failure rates from something with a cycle testing or something that was moving multiple times per hour. Make sure that it comes from a reliable source, something like Rigor or FMEDAs, silsafedata.com, the SCRH. Make sure that the failure rates make sense. If you question if your failure rates are making sense, I always call silsafedata.com my sanity check. It has a bunch of generic devices like a floating ball valve and will give you a range of where to expect your failure rates to fall in from. Usually it's a large range because those devices could have a large variance of complexities. However, it can give you a warm and fuzzy feeling if your failure rates are in the right ballpark or way out of expectations. So As I said a little bit earlier, if you're doing the things we talked about in that integrated design, the engineering calculations, the torque curves, you're doing what proof testing should be done for the final element assembly, there can be a failure rate discount, and it can be realistic depending on how far you are going with your integrated assembly. Now, this can be done on a standard product or a design-based product. So this could be for a standard off-the-shelf product of this valve always with this actuator, always with this solenoid in this nice package. Here's your certificate with these failure rates always associated with them. However, that's not how the world always works, and we understand that. So we are using the same process and procedures that we use in certifying a bespoke device or a custom device. We follow the same process and procedures from the standards, but for the integrated process. This can be done from the OEM side, which is normally what we see. The OEM saying, hey, we're already making this valve or this actuator or this valve and actuator. We want to increase what we can offer for our customers. We want to take some of their pains away from them, do the calculations for them, and offer a great solution. However, we've seen it from other ways as well. We've had valve integrators call us up saying, hey, we want to buy this valve, this actuator, this solenoid, put it together and offer it in a package. Or even end users saying, we have this package, we want to look at it from an integration standpoint. No matter how you look at it, all the requirements from the standards are going to be the same. No matter if it's the IEC 61511 or 508, they're going to be complementary of each other. There's going to be traceability needed, documentation needed, and to get that information to your customers through the means of a safety manual. If you like this information and want more details, a lot of this is covered in one of our newer books out there, not the newest, but one of them, but the final elements in safety instrumented systems. Chapter 15 on verification, we talked chapter 16 on failure rates, data, chapter 17 on applications, and chapter 18 on that final element, bespoke systems. So if you have any questions, I'm going to go ahead and take some now because, of course, I didn't stop. I was on a roll. Sorry about that. And if you think of any, while I get that up and loaded, if you think of any later, please feel free to email me. Check out all of that great information, the white papers, the webinars, blogs, our books, all of that reference material we have out there. And if you've really, really enjoyed this, we have more. If you want to really dive into functional safety, alarm management, or cyber, we have detailed classes. Some classes are a day, some classes are up a whole week, and they're all over the world. And we actually have started online training now as well. So if you can't make it to one of those and still want training and to get more into functional safety, check those out. Okay, so the first question we have, let me blow this up a little bit. The font is very small, sorry. Okay, so we know that during the Macondo or the BP Horizon accident, the final element, the blowout preventer, failed to isolate outflow since a deformation occurred in the BOP assembly when leakage started. How can we assure that a SIL certified final element can properly do the job when it may be subjected to unforeseen different specific conditions when the accident occurs? Considering that all unforeseen conditions cannot be simulated during proof tests. And this is absolutely a great point. When it comes to functional safety, we're trying to manage risk as best we can. When we have somebody that comes to us and says, well, we want to manage all risk, we want no risk at all, we want to guarantee we're safe, we simply let them know that you cannot open the doors. Don't open your process, never start up. That you cannot eliminate all risk. You can't foresee everything that can happen. We just try to do as much as we can. And unfortunately, from each accident, we learn more and more. Even if having all SIL certified final elements in that specific condition, that wouldn't have prevented this specific accident, or this specific accident. Unfortunately, when all of the analysis was looked, there were issues with safety culture, there were issues with proof testing, there were issues with maintenance personnel saying they replaced damaged devices when they didn't. There was a number of issues that kind of built up like that Swiss cheese model. You're never going to figure out everything for a specific hazard or location, but try and look at the similar conditions, similar operations, find out what we know from close calls or similar accidents, and try and use as much information as we can to just make the world safer. The next question we have, does IEC 61508 or IEC 61511 mandate third-party certification for final element certification? I have seen end users accept manufacturer certification as is, and a lot of those numbers are very optimistic. Yes. So there's a kind of multiple questions in this. First of all, the standards, either IEC 61508 or 511, does not say a third party has to be used. It says it's up to the end user and the device manufacturer for that to be agreed upon. However, it does say you need to have realistic information. And the new versions of IEC 61508 and IEC 61511 made their wording much stronger because of issues just like you're speaking of, whether it's manufacturers only counting their returns and not thinking that there could be things that weren't returned for them, or something like using cycle test data. There's a number of ways to get overly optimistic failure rates, and unfortunately, the law does not say you cannot use them. It says you need to use failure rates appropriate for your application, appropriate for your environment, appropriate for your operation. They need to be traceable, they need to be logical, they need to be credible and justified. However, it doesn't say it must be done by a third party. It's highly recommended, but that's not the case. For yourself, I would always say use silsafedata.com and check against that as your sanity check. If you do receive failure rates that are overly optimistic. Use generic failure rates or those kind of that top level of the silsafedata.com to kind of, that would make me feel better and sleep better at night. It might be a little conservative, however, you're not going to be ridiculously optimistic. The next question we have is, does exida have failure rates for coupling, brackets, things like that? Yes and no, depending on what type you're talking about. We have failure rates for things like low stress parts and mounting brackets, absolutely. However, if this is mounting that the neighbor down at the shop is just taking a scrap piece of metal, bolting it on, not calculating the stress strength, that's a different point of view. That's something completely different. Unfortunately, we see a lot of people using that scrap metal, a bolt, saying it's good to go, sending it out. And that's not the same. But yes, if you do want to, I believe in our EMCRH data, it has information for all of those type of failure rates. So the next question, unfortunately, I'm not going to give you the type of answer you're going to look for. Would you please recommend a frequency for the validation and the proof testing in the field for both sensors, logic solvers, and final elements? Unfortunately, this is a lot to do with the condition, the operation, the application, the environment, and the devices in play. It depends on what type of proof testing you're going to claim and how much coverage you're going to claim with that. You could do something like a partial valve stroke test every even couple of weeks just to prove a tiny bit of movement. You're not going to get a lot of proof test coverage from that. However, you're going to not have to do a major proof test more often. This can be a very large answer that can depend on a lot of variables. We actually have webinars on proof test recommending proof test duration and the different levels of proof testing that we've done one not too long ago since the beginning of the year that I would recommend looking at. And if you have more questions, feel free to email us and we can talk about what specifics you're looking at and more information. That's all the questions I have for now. If you have any later, please feel free to let us know and always check back. We are going to continuously have more blogs, more webinars. Check us out through LinkedIn and Twitter. Thank you so much for joining us today. Have a good one.